Thanks for the invitation to give this talk. So I'm interested in indirect detection of axions using astrophysics. And if you think about actually the constraints on axions that are the strongest today, they're all coming from astrophysics. And of those, a large portion of them are coming from somehow producing the axion or converting the axion in the vicinity of a star. And so it's interesting to think about what you can do with stars because they provide very strong constraints on axions. So that's what I'm going to be talking about today. So I want to give a brief introduction to what is an axion. People have already talked about it, but the axion is a hypothetical fundamental pseudoscalar particle. And if it's the QCD axion, it can solve the strong CEP problem and make up dark matter. And Laura gave a nice overview of this yesterday. There are also a related class of axions which appear in the context of quantum gravity constructions. So there's this notion of the axiverse where you might produce many hundreds of axions in compactification processes. And these axions would, probably exist as a related class of axions if the QCD axion also existed. And these are very strongly coupled and low mass axions that often you can produce very easily in hot, dense environments like, for example, stellar cores. All that's really going to be important for me, though, is that axions, whether it's the QCD axion or axion-like particles, I'll use that interchangeably, they couple to matter and electromagnetism. So they couple to matter with a derivative coupling that is indicative of the shift symmetry of the axion, with a coupling given by GAFF, where F runs over standard model fermions. And they couple to electromagnetism through the AFF dual operator, which couples A and E dot B, essentially is what this is if you expand that out. And the coupling strength there is given by the axion-photon coupling, which has units of inverse energy. So what can you do with these? Well, both of these operators give you ways to produce axions in stellar cores, for example, through scattering processes that might take place in, for example, white dwarfs or neutron stars. You can Bremsstrahlung axions using this operator. And as I'll talk about more today, with the electromagnetic operator, you can also produce axions. Finally, this additionally allows you to do things like convert axions into photons and vice versa in the presence of external magnetic fields, and this can be a useful way to detect these axions directly in, for example, a laboratory setting. So when you think about things that you can do at stars to probe axions, this is definitely by no means an exhaustive list, but it's some of the kinds of things that I've personally thought about. So you, like I said, can produce axions in the cores of stars, and they're actually astrophysically very similar to neutrinos in the sense that they're low mass and weakly coupled. So once you produce them in the core of a star, they free stream out of the star because of that weak interaction and act as an additional source of stellar energy losses. So here are some examples of ways you can constrain this energy loss through stellar evolution. And I'll talk about this R parameter in a second. You might also think, maybe you can not only just consider the effect on stellar evolution of this energy loss, but maybe in some external magnetic field, you can actually directly detect the photon that the axion converts into. And so, for example, this is the idea behind the CAST experiment, and also some indirect detection schemes that I've worked on in the past couple of years. One thing I'm particularly excited about recently, I've been thinking about in the last year, is the idea that you can essentially probe the survival probability of photons as they free stream away from the surface of the star through the magnetosphere of a star and convert into axions, in particular through polarization probes of white dwarfs And people have worked on somewhat similar things in the radio bands at neutron stars. And I should mention this isn't by any means an exhaustive list. It's just some of the kinds of things that I've worked on. From this conference, people have already presented work on other mechanisms, and also will tomorrow. So I want to focus on this R parameter here because it's a really strong bound and gives kind of a flavor of the sorts of things you can do with stellar evolution probes of axions. So the basic idea is, if you want to learn about stellar evolution, it's really nice to look at a globular cluster, which is essentially a gravitationally bound cluster of many stars. And all of the stars have basically the same age in the cluster. And for globular clusters, this is basically order of Hubble time, so 13 gigayears or so. And it's interesting to ask if axions can modify any of the stellar evolution that's taking place in this cluster. I should mention, just because of the range of masses of stars in the cluster, you'll have a wide variety of stages of stellar evolution present. So in particular for what this R parameter is, you're going to be interested in looking at basically how long-lived is the horizontal branch stage of stellar evolution relative to the red giant branch stage. So I just want to make sure everyone's on the same footing. I want to explain what a red giant star is, and essentially it's the next stage of stellar evolution for our sun. So our sun is currently burning hydrogen in its core, and in about 5 gigayears, it's going to run out of core hydrogen, and a degenerate helium core is going to develop in the center of the star, and it'll become a red giant star. And you can basically think about this, it's like a helium white dwarf just embedded in the star. And how this thing evolves is you have hydrogen burning in a shell around this helium core, which heats it, and at some point it heats it up enough that it spontaneously ignites helium in an event known as the helium flash, and this happens essentially immediately on astrophysical timescales. It's about 10,000 years, depending on exactly what you mean by the helium flash. This leads this star onto the horizontal branch, and this is characterized by a helium-burning core with a hydrogen envelope. So the difference between these is this is a degenerate helium core, this is a non-degenerate helium core that is actually burning helium. And now you can ask, is there anything that axions can modify here? And the answer is yes. So you can have processes, if there's a non-zero axion photon coupling, that look like this. So you have ambient photons in the core of the helium star, in the helium core, and these can convert into axions using the Coulomb field of the charged species in that core. And the cross-section for this, like everything else in axion astrophysics, was worked out by Rafelt in 1980. And basically, the result, when you sort of integrate over the entire core of the star, is that lifetime that the star spends on the horizontal branch is reduced by this factor. So 80 here, this is coming from the fact that on average, the horizontal branch core generates about 80 ergs per second of nuclear energy losses, or nuclear energy, in the absence of an axion. In the presence of an axion, you add 30 ergs per second for an axion photon coupling of 10 to the minus 10 inverse GeV, and it scales like this coupling squared. So this affects the helium, or the horizontal branch stage of evolution, but it actually doesn't affect the denser red giant branch cores. And the reason for this is that since they're much denser, the photon has a large plasma mass, and you don't really get photon propagation here, so this process turns off. And so then if you go back to this picture and imagine what happens if you add an axion in, is basically the core of the star contracts because of this energy loss, and the reason is that these cores have negative heat capacities. So if you actually add in energy loss, if the core loses energy, it actually heats up because it has to contract and burn more nuclear fuel to compensate for the energy loss. Okay, so then you can go out and look at globular clusters in the galaxy, for example, and compute this R parameter, which what it is the number of horizontal branch stars in the globular cluster divided by the number of red giant branch stars, and has a rough analytic expression here that isn't too important, but the basic point is that because essentially the horizontal branch stage is shorter in the presence of an axion, if you have a larger axion coupling, this decreases the R parameter. You have to be a little careful because this can be offset by an initial larger initial helium fraction in the star, which means that it just takes longer to burn through all of the helium in the core. So that's what this Y is the mass fraction of helium. But you can compare to data, and this was done by this group here almost 10 years ago, and they found this extremely strong constraint on the axion-photon coupling that had to be less than 0.66 times 10 to the minus 10 inverse GeV for axion masses less than 10 keV. And this cutoff is given by the fact that helium burns basically at 10 keV. So if you have an axion with a mass larger than that temperature, you can't do this production mechanism. It's just kinematically disallowed. So now I want to think about not just probing this energy loss, but actually maybe directly detecting the presence of this axion through its coupling to photons. And one of the interesting ways to do this is through this experiment called CAST, which ran for about 15 years starting in 2003. And the basic idea, also, again, like everything in Axion astrophysics, was developed in the 80s. The basic idea is to look for this Primakov production of axions, the same thing, but in the sun. So the sun's obviously a lot closer. If you want to directly detect something, that's where you want to look. So you can integrate over the whole sun. It's relatively well understood through things like helioseismology. And the flux spectrum of axions that you get is about 10 to the 11 axions per centimeter squared per second keV at Earth. So, you know, about the size of your fingernail, there's 10 to the 11 axions going through for this axion-photon coupling, which is it's the same one I was showing earlier. And this spectrum, shown here, peaks in X-ray energies. The reason for that is that the core of the sun is approximately 1.5 keV. I should note there are other production mechanisms if the axion couples to electrons, for example, and they're shown here. But I'm just going to focus on this Primakov production. And the idea of CAST is to build this thing that's called a helioscope, basically an X-ray detector, but you set it up so that you could only see axions that convert in some magnetic field. So the setup is you have some wall here that stops surface X-ray photons from the sun getting through. This is actually a picture of the X-ray sun. But what can get through is the axions that are emitted with X-ray temperature or X-ray energies. And then you have a magnetic cavity. This should be 10 Tesla. It has a magnetic field of about 10 Tesla and a length of about 10 meters in which you can convert the axion into a photon. And then, assuming this conversion happens, it's detected at some detector on the other end of this magnetic field. And basically, you set this thing up so that it kind of follows the sun at sunrise and sunset and tries to look for these axions. So the conversion probability in this case for a uniform magnetic field is given by the axion-photon coupling squared times the magnetic field of 10 Tesla squared times some length scale. And you might think you can just plug in this length scale, and that's true for low mass axions, but it's not true if the axions have a relatively large mass. And the reason for that is essentially the axion photon system, as it propagates through this magnetic field, the axion and the photon can go out of phase if the axion has a large momentum. So this is suppressed by the momentum difference between the axion and the photon, and at masses larger than about 10 to the minus 2 eV, the conversion probability is suppressed by ma to the minus 4 power. So if you put in numbers for a zero mass axion, then the conversion probability is given by, is about 10 to the minus 17 for the same axion-photon couplings. And this is extremely low, but remember that we're actually seeing 10 to the 11 of these per centimeter squared second. So you could think that this might actually work. And if you compute the number of axions you expect to see, you multiply these two things we computed on the previous slide, and this area of cast, which is, I mean, it's basically the effective seeing area, and that's about 30 centimeters squared. And this gives you 10 to the minus 5 counts per second per keV in your detector. And the final run of cast accumulated over 1 million seconds. And so if you just multiply these things together, you can basically see that for this axion-photon coupling, you might actually be able to see some axions. You should have some maybe order 10, 100 in the detector over these 15 years. This is the final constraint that the cast collaboration produced, which actually, by numerical coincidence, just is the same constraint that we obtained from horizontal branch stars, 0.66 times 10 to the minus 10 inverse GeV. But you can see that at about 10 to the minus 2 eV, the conversion probability becomes inefficient, and the limit actually scales like 1 over the axion mass after that point. There's a successor now people are building at DESI called IAXO, and it's going to be a significantly improved version of CAST. So it'll have kind of a similar magnetic field, but it'll be twice as long. And the really big improvement is that the seeing area is 4 meters squared instead of about 30 centimeters squared. And in combination with having much lower backgrounds, this is going to significantly improve the constraints that you're able to get through these helioscopes. So the baby IAXO prototype constraints are here, and that's being built currently and should be taking data around 2028. And then there's a full-scale detector and an extended detector that, in terms of flux, will do about 5 orders of magnitude better than CAST. So now I want to move on to something that I'm really excited about, which is the idea that we can look for excess polarization of white dwarfs coming from photon-axion conversion in the magnetosphere. And the basic idea is that magnetic white dwarfs emit thermal unpolarized radiation from their surfaces in the optical, typically, depending on the temperature of the white dwarf. And if these white dwarfs are magnetized, then the component of that thermal radiation that's polarized parallel to the direction of the magnetic field can convert into an axion, which is then just unobserved. By contrast, the component of the polarization polarized perpendicular cannot convert because of this A dot B coupling. And so at the end of the day, what you see at Earth is actually a linear polarization polarized perpendicular to the direction of the magnetic field on the white dwarf. So this is really looking at some survival probability, but it's phrased in terms of linear polarization just because only one polarization can actually convert into an axion. And so to make this a little more quantitative, you can write down some unpolarized vector potential, and if the axion photon system's traveling in the x3 direction, the magnetic fields in the x2 direction, then the value of this vector potential in the x2 direction will be depleted by a factor of 1 minus the linear polarization at Earth. And so now you actually want to compute this thing that's fairly similar to what you expect from CAST. So the Lagrangian we have in mind is some axion photon coupling A E dot B, where B is now taken to be the background magnetic field supplied by the magnetic white dwarf. And it's easiest to just analyze this in the context of a dipole magnetic field model, although we actually do things numerically in our paper. And you can write down the axion photon equations of motion, and as you expect, it mixes the axion and the component of the photon polarized parallel to the magnetic field. So in this mixing matrix here, the off-diagonal terms are the ones that are doing the mixing, given by G times B. And for a dipole magnetic field, B falls off as 1 over R cubed. And this on-diagonal term, which is coming from essentially the mass of the axion, can suppress your mixing at high axion masses. And this does happen for masses above about 10 to the minus 7 eV for the white dwarfs that we're looking at. But you can compute this exactly for a zero mass axion in a dipole magnetic field. And what you find is that the linear polarization is about 10 to the minus 4 for axion photon couplings of 10 to the minus 12 inverse GeV. So this is smaller than the previous ones that I've been taking. For typical white dwarf parameters, so a magnetic field of around 100 megagauss, which you can expect at some white dwarfs or even higher, and a stellar radius of around an Earth radius, which is also typical for these white dwarfs. The reason that this is so much larger than what CAST was getting is basically that this magnetic field is much, much larger. Okay. So now we know what we should expect to see at these magnetic white dwarfs. We can go out and look for magnetic white dwarfs that we can actually use and to look for evidence of this process. It turns out that highly magnetic white dwarfs are very rare. So if you look in the literature, you'll see something like 20% of white dwarfs should be magnetic. But what they really mean is, they might have kilogauss fields or so. But what you need for this process to be efficient is several hundred megagauss. And these several hundred megagauss white dwarfs are rare. There's 10 of them. They're all listed here with magnetic field measurements, 10 of them known anyway. And of those, the available archival data on linear polarization of these white dwarfs is even scarcer. So only 3 of these have archival linear polarization data. And I'm just going to take a look at this one called SDSS J1351, because it ends up giving the strongest constraint. Although the other 2 are interesting in their own right because they have sort of additional things going on. So the SDSS collaboration fit the magnetic field of this white dwarf with a dipole magnetic field model. And this model has 2 parameters, has a polar magnetic field strength and a inclination angle with respect to the line of sight to Earth. And just numerically, basically what you want to do is take the white dwarf, there's some observable hemisphere, that's the side that's pointing towards you, and you want to compute the linear polarization that you expect from all of the points on this surface and average that to get the overall linear polarization expected from the entire star. And when you do that, what you find is that the linear polarization scales like B naught squared times sine I squared. So at inclination angles of 0, that is the dipole axis is pointing directly towards Earth, you have a cancellation and you get actually no effect at all. But the SDSS collaboration fit this white dwarf flux data to this magnetic field model and found at 68% confidence these orange contours that are shown here, which indicates that the white dwarf has a magnetic field of about 700 megagauss and a fairly substantial inclination angle. In our paper, we just take the most conservative values at 68% confidence that you possibly could. So an inclination angle of about 50 degrees and a field of about 700 megagauss. And then you can just read off from this plot that you expect a linear polarization of order 0.04% for these values. And now what you want to do is actually compare this expectation to data. So there was a Russian telescope called SOA that observed this white dwarf in the optical, looking for linear polarization. And this data set is reproduced here on this plot. So I'm showing the linear polarization of the star as a function of wavelength in angstroms. So this is the optical. And basically we fit three components to this data. One is the axion contribution. So the axion contribution is energy independent. That is, in the linear polarization equation, there was no energy dependence that came in anywhere. There's also an astrophysical contribution to linear polarization that I didn't have time to talk about, but basically arises from transitions in the atmosphere of these magnetic white dwarfs. And an example of this looks like this for this star. It's highly featured because there's things like hydrogen absorption edges and transitions in the magnetic field that kind of get averaged. Things get smeared out as you average over the surface of the star. The magnetic field changes over the surface. So that's why you get kind of this highly featured model. And the third component to this fitting is a systematic that is completely degenerate with the axion model. And the reason that we incorporate this is that this telescope has some intrinsic polarization. So that is, if you point it at an unpolarized source, it can tell you there's actually some polarization there, and it's very hard to get rid of this excess polarization. You can do things like look at unpolarized stars to try and remove some of this, but it's relatively hard, and this systematic is there at the level of 0.4%. So we also include in this fitting procedure a component that is completely degenerate with the axion model, but has a Gaussian prior on its normalization of mean 0 and variance 0.4% squared. The reason that it's completely degenerate with the axion model is that this is the absolute most conservative thing we could do. If you gave it, for example, some energy dependence, then it's going to be, the fact that it's less degenerate with the axion model is going to give you stronger constraints, actually. And so if you go through fit this data using, for example, a profile likelihood, you'll find that at 95% confidence, the axion contribution has to be less than about 1.25%. And now, using the expectation that we derived here, you can write down constraints on the axion-photon coupling, which are given in sort of this dark orange here. So at 0 axion mass, you end up with an axion-photon coupling of around 5 times 10 to the minus 12 inverse GeV. And this cuts off because of the high mass effects that I mentioned earlier, around a few times 10 to the minus 7 eV. So this is one of the strongest constraints on axions, especially in the sort of nano eV to micro eV range, and actually excludes this thing. I didn't have time to discuss this, but excludes this anomaly called the TeV transparency anomaly, which has an axion interpretation. So this excludes the axion interpretation of that anomaly, so something else should be happening. So just to wrap up, I hope that I've shown you that stars are extremely powerful probes of axions. Most of the strongest constraints on axions to date come from some observation of stars. And I think that this polarization search at magnetic white dwarfs is sort of posed to be one of the strongest constraints on axions now and in the near future. So there's that list of 10 magnetic white dwarfs that most of them don't have linear polarization data. And I'm working with an astronomer, Alex Filipenko. Oh no. Alex Filipenko at UC Berkeley to obtain dedicated observations in the optical of as many of these magnetic white dwarfs as we can with Lick Observatory, which should do much better than basically the archival linear polarization data that's currently available in previous literature. And so I'm hoping that in the next couple of years, probably be a long process, I'll have something to say about that. So, yeah, thanks for talking.
Thank you very much for a nice talk. I wonder if in the binary system of a white dwarf and a neutron star, the axion could interact with the magnetic field of the neutron star, and will it be like detectable, or is it wipe out the effect? What do you think?
Yeah, this is a super interesting idea, actually. I was thinking about this a couple years ago, and I think we didn't find any binary stars that have the correct geometry. So basically what you need for this to happen is you have some white dwarf like here, and the Earth has to be collinear with a neutron star so that you produce, I mean, you can do this multiple ways. You can produce axions at the white dwarf, and they free stream through the neutron star magnetosphere and convert in the magnetosphere the neutron star. Yeah, it's an interesting idea. I don't know of any cases where this actually works in practice, but you can also, for example, produce axions inside the cores of neutron stars, and those can free stream out of the star directly, and then those will go through the magnetosphere, convert into X-rays, and you can look for those, and that's actually something I've done. Yeah.
Thank you.
Hi, thanks for the nice talk. Can you expand a bit more about the systematics that you brought up? So you mentioned for this conversion, there's already some polarization. So I'd be curious to hear a bit more about that dashed line.
Yeah.
And also, the second part of the question is for the instrumental polarization. I'm a little confused. Like, if you're just picking, like, how do you pick this Gaussian 0.4? If it's completely degenerate, doesn't that completely set your bound? Like, how well is that characterized? If it were not 0.4, but say 1.2, that would change your results.
Yeah, so with regard to the systematic, unfortunately, it's hard to say too much about this because we don't actually have access to the data itself. This is just taken from this paper, and this is actually one of the reasons we're working with the Lick Observatory, so we can have access to sort of the raw data and understand these things better. So yeah, the system, basically the observers on this telescope have observed lots of unpolarized stars, and they observe a scatter of about 0.4%. And that's where this number is derived. Yeah, it could be different. It could have some energy dependence. We just don't know. And yeah, we just essentially took this number, and this is the most conservative thing you can do with it, is make it degenerate with the Axion model. It could be slightly larger, and that would affect things. But the constraint scales like the polarization to the 1/2 power, so it's relatively insensitive. But this is something we're hoping to better understand at the Lick Observatory. Sorry. With regards to the astrophysical polarization. Yeah, so the photons propagate. They're initially produced unpolarized because they're thermal from deep in the magnetic white dwarf atmosphere. And basically the dominant continuum background polarization production is from ionization of hydrogen atoms. And this is pretty uncertain in the magnetic fields that are present on the surface of these white dwarfs. So at zero field, you know the cross section for this to happen. At 100 megagauss or so, basically what people do in the literature, and this is actually observed to be a relatively good fit to linear and circular polarization data, is just use the linear Zeeman effect. So replace this omega, which is the frequency of the photon, with omega minus q times the cyclotron frequency, where q is the difference between the initial and final quantum numbers of the electron. And so this leads to a linear polarization that scales like b transverse squared omega squared. But what actually ends up dominating is you have these regions near hydrogen absorption edges, and this gives you some essentially very variable linear polarization. And the location of these edges is highly dependent on the magnetic field. And so that's where you get all these features from, basically, is these are coming from hydrogen absorption edges. And these are at known wavelengths.
Thank you.
So building up on the first question, and actually on your last comment on the action production in neutron stars. So in principle, given that magnetic fields are higher, I would naively expect that those are more promising targets. So why isn't that if it is not?
Yeah, so good. There's kind of a couple reasons. One is that this actually scales like b squared times the radius of the star squared, and this is much smaller. So it's not quite as nice as you would naively think, but there's another kind of more complicated reason, which is that at super large magnetic fields, and this didn't really apply for magnetic white dwarfs, but for, say, 10 to the 13 Gauss, you have nonlinear effects that arise from basically integrating out the electron, and this gives rise to a photon index of refraction. So this term was previously 0. Now it's basically, you can think of it like a photon mass of order omega squared times b squared. And actually what happens is at large magnetic fields, since this guy goes like b squared and this guy goes like b, it dominates. And kind of at the end of the day, for neutron stars, the scaling in the regime you're in only goes like b to the 2/5 power. And the combination of these two things makes neutron stars actually not as interesting for polarization studies, at least. This also happens, of course, for axion production and subsequent conversion, but basically because of the radius effects, they're kind of similar conversion probabilities.
Okay, thank you. And I have well, actually, it's a curiosity concerning these helioscopes. So the time scale for the limits is like a month. So why is that? So the observation time for the limits, for instance, with CAST.
Oh, with CAST.
So it's like a month. So
yeah, right. So I'm not. The main limiting factor is that you actually, like, this is a really heavy tube of, it's an old CERN magnet that you're using, and the main limiting thing is that they only look at the sun during the sunset and sunrise. So I think it's a total of about an hour every day, and then they didn't actually run it every day for 15 years. It was in some combination of, I think, 3 runs. And yeah, at the end of the day, you only get like a total month.
Thanks.
Any more questions? I'd like to thank Chris again.
Thanks.